Question 2. Gas exchange. 3 properties with a reason. Lovely. Magic. So you can think of 4 or 5 properties of gas exchange surfaces. Thin, large surface area, permeable, maintaining a gradient, quite often moist. So just reel them off. So let's go for the easy ones first. Let's go for thin, and we'll have short diffusion distance. Let's have large surface area. Always say surface area, don't say SA. Could stand for anything. And that means there's a large area for diffusion, gas exchange. So, large area for diffusion. And what else would be, because this is all respiratory surfaces, so not all respiratory surfaces will be ventilated and maintain their concentration gradients possibly. So let's go for another easy one. Permeable. To allow gases to pass through. To allow gases to pass through. So pretty straightforward 3 marks. We got a frog, flat-headed frog, found in fast flowing, there's a clue, streams, and is the only known lungless frog, so it hasn't got lungs. So what do we know about frogs already? We know tadpoles have gills, and we know the adult frogs do gas exchange across their body surfaces or have simple lungs when they're active. So how this frog carries out gas exchange without lungs, it's just straight from the notes, and that's across the body surface. Usually when it's not very active. How do the conditions in the mountain stream aid gas exchange? This goes back to, we mentioned it already, maintenance of a gradient. So if you've got fast flowing water, brings oxygen over this surface, and we'll get rid of water that's got CO2 in. So fast, noticing it's fast flowing water maintains this concentration gradient. Concentration gradient, for gas exchange. 2 reasons why gills do not function effectively on land. So if you get fish, it'll flap about on land for a bit, but it can't extract much oxygen from the air. Why? Well, when you dissected the gills, when you got the gill out, you had to put it in some water to see it really, or else it just kind of clumped up in a big red blob. And so that's what happens, and then there's not much surface area for gas exchange then. And also they eventually just dry out, and gas exchange won't be flexible, and gas exchange won't be possible across a dry and crusty gill. So those are your 2 answers. So let's put that one first. They dry out, and the other one, they'll clump together, because of surface tension and collapse on top of each other. They clump together, or you could say collapse. So good so far. It's just quite a lot of theory really in this AO1 style. Define countercurrent flow. Brilliant. In the gills of bony fish, and explain why counterflow makes it efficient. And we need 4. So 3 things immediately pop to mind in the sentence you're going to remember, and then maybe the advantage of that, maybe the 4th. So the phrase that you'd always remember is blood and water move in opposite directions. So let's say that first. Blood and water move in opposite directions. It has to be opposite, not different. It has to actually be opposite. And the advantage to this is it maintains the gradient for gases across the entire gill. Or there's always, higher oxygen water than blood. So maintains the gradient for gases across the entire gill plate or gill MLA or whatever. So we've got possibly 2 or 3 there. So what else can we say? I think that's at least 3. And then what's the eventual advantage as opposed to a non-bony fish? Well, this, you might remember the graphs where the non-bony fish, there's an equilibrium at kind of 50%, whereas with countercurrent flow you can get up to 100%. So this enables a higher saturation of blood with oxygen, enables a higher saturation of blood with oxygen.